Hello, welcome to the ninth class of this course. So in the last class what we did is basically we took the Legendre differential equation. This is the Legendre differential equation and we solved it. So we found this recurrence relation. This is the recurrence relation we found, and this is the general solution, which consists of two series. One has the finite powers, one has even powers of x, another one has odd powers of x. Okay, so let me write it as YL even, and let me write it as YL odd. Okay, and why I am writing it as L? What's the significance of this L? It's because depending on L, different values of L, you will get different solutions. So the solution is indexed by L. Okay, now what we got is basically we got two linearly independent solutions, that is Y even L and Y odd L. Now the both are power series, infinite series. Okay, now the question is, does the series both this Y even L and Y odd L converge at all values of x? Okay, so does this series converges for all values of x? So to check whether the series will converges at all values of x, what we need to do is we need to do first ratio test. Okay, and this is the recurrence relation. So for this YL series, what this recurrence relation does is it basically connects nth term with n plus 2th term, right? But if you look at either of these even or odd series, this recurrence relation connects between two consecutive terms, right? Because this is the second term and this is the third term for this even series, but here it is just n equals to 2 and n equals to 4, right? So a4 and a2. So what I'm trying to say is basically for either of these series, the ratio we should be concerned about is the ratio of two consecutive terms is basically this factor, which is an plus 2 divided by an, right? This is this factor. Okay, so that is this factor, so that is minus L minus n times L plus n plus 1 divided by n plus 1 times n plus 2. Okay, and between two consecutive terms of either of this even series or odd series, x has a power difference of 2, right? So it will be x square. This is the ratio between two consecutive terms. So what, so if I call it R, which is basically limit n tends to infinity mod of this ratio equals to limit n tends to infinity, I can write it as mod of n minus L, n plus L plus 1, n plus 1 n plus 2, and I can write this x square outside. I'm assuming x is a real number, so in that case x square is always positive, so I can put it outside the mod, and it is I can write it as limit n tends to infinity 1 minus L by n times 1 plus L plus 1 divided by n divided by 1 plus 1 by n 1 plus 2 by n mod x square. Okay, and as n tends to infinity, this value will be 1, right? Because as n tends to infinity, L by n will tends to 0. This term also will tend to 0. This also will tend to 0, and this also tend to 0, right? So basically what we have is this r equals to x square, right? And so for x belongs to minus 1 comma 1, x square less than equals to less than 1, which means r also less than 1, and the ratio test says that the series will converge. So converge. X, if x greater than 1 or x less than minus 1, in that case x square will be greater than 1. It implies that will imply r also greater than 1, and that will imply that the series will diverge. Okay, and if x equals to plus minus 1 or x square equals to 1, or rather r equals to 1, which means that the test fails. Okay, so the ratio test, so this is what I am doing, the ratio test. So the ratio test is saying that the series, both these even series and this odd series, they will converge when this is x equals to 0, this is x equals to minus 1, this is 1. Okay, so in this open bracket of minus 1 and 1, here in this region the series will converge. Okay, in these regions the series will not converge. And it cannot say anything about these points, plus 1 and minus 1. Okay. So naturally the question will arise that what happens at x equals to plus minus 1. Okay, and why we are interested in x equals to plus minus 1? It's because whenever in real problems, whenever you will deal with real problems in theory, for example hydrogen atom problem and all, so there in terms of this x you will basically get this cos theta or sin theta or cos phi sin phi. So there basically this cos theta, it can take values like plus 1 minus 1, right? Sinusoidal functions, it can take values plus 1 minus 1. So basically we will find those solutions, we are interested in those solutions which does not diverge at x equals to plus minus 1. We are interested in those solutions. Okay, so that's the motivation behind investigating at what happens at x equals to plus minus 1. Okay, so the question is now, what about x equals to plus minus 1? What about these points? Okay, let me check for, check for L equals to 0, right? And I will consider even series and odd series separately. Okay, I will test the convergence of them. I will talk about the convergence of this odd series and even series separately. Okay, so let me first look at this even series. So you can see that here this L is multiplied with all like higher order terms except this one, you know. And if I put L equals to 0, then basically this even series, it's not a series anymore. It is basically truncated because all the other terms are 0 except this one. Okay, so basically it becomes a constant, or rather for generalization I can say it becomes a polynomial. Okay, the series we can, so polynomial means, what do you mean by polynomial? So let me write down again, polynomial. So if I write it by p of x, which is basically sum over n equals to 0 to n a n x minus x naught to the power n. Okay, where this n, this capital N, it's a finite number, it's not infinity. That means a polynomial, for a polynomial it has finite number of terms, it is not an infinite series. So if it's an infinite series, if the terms, so if n goes to infinity, then I can call it a power series, right? But if I can truncate the series as I'm doing here, okay, as I'm doing for this even series, so all other terms except this one, 0, right? So that means we're truncating the series and now we have finite number of terms, then I can call it a polynomial. Okay, so this n is finite. Okay. So in that case our even series y even L equals to 0 equals to 1. And it is finite, so we can work with this even series for L equals to 0. But what about the odd series? Does it converge? Let's see. So for L equals to 0, the odd series is x minus. So if I put L equals to 0, then it is minus 1, and this minus there will be plus then. So minus 1 times 2 and divided by 3 factorial. So that means it's 1 by 3. It is plus x cube divided by 3 plus again if I put L equals to 0, in that case it will be, there is a minus 1 here, there is a minus 3 here, so minus plus. Okay, and then it is 1 times 2 times 3 times 4. Okay, it is 4 factorial divided by 5 factorial. That means it is 1 by 5. It is 1 by 5 times x to the power 5 plus, if you can follow the pattern, then it will be x to the power 7 by 7 plus dot dot dot. Okay, so this is the odd series for L equals to 0, right? Now what happens at x equals to 1? It is 1 plus 1 by 3 plus 1 by 5 plus 1 by 7 plus dot dot dot. So now we need to check whether this series is and whether this series converges or not, or diverges. So in order to check that, so we already did the ratio test and it fails for x equals to 1. So we need to do some other test, and the test I'm going to do is called the integral test. Okay, so what I will do, let's say this is 1, 2, 3, 4, 5, 6, 7, right? So this is 1. It is not scaled properly, but for example, let's assume that it is 1 by 3. Let's assume that it is 1 by 3 for y-axis. Okay, for the time being, let's assume that this is 1 by 5. Okay, similarly, let's assume that this is 1 by 7. Okay, okay. So what about this area? What about this area? This area is 1. This area is 1, right? 1, here this length is 1 and this length is also 1. What about this area? What about this area? This is, so this height is 1 by 3 and this length is 2, right? So it is 2 by 3. So the total area is 2 by 3. Plus, if I add this area, then it will be plus 2 by 5, right? Then if I add this area, then it will be plus 2 by 7. Let me call it capital A. This is our A, plus dot dot dot, plus dot dot dot. Okay, so there will be other terms. Okay, and I can write it as minus 1 plus 2 plus 2 by 3 plus 2 by 5 plus 2 by 7 plus dot dot dot. Okay, plus to minus 1 plus 2 times 1 plus 1 by 3 plus 1 by 5 plus 1 by 7 plus dot dot dot, right? So it is basically, so A is basically minus 1 plus 2i's y odd x equals to 1, L equals to 6. Okay. So if I can show that A is convergent, then I can say, okay, then this series is also convergent. Or if I can show A diverges, then it follows that, okay, this series also diverges. Okay. So it's all about showing that whether this area converges or diverges. Okay. So now you can understand a little bit like why we are interested in this integral test. It's because we are dealing with area. Okay, so now let's define a function which looks like this. So it passes at these points, it passes through these points. So at x equals to 1, its value is 1 by 3, at x equals to 3, its value is 1 by 5, and so on. So this function so what will be the functional value then? Let me call it fx. So what will be fx then? Let me write it 1 by x, and so at x equals to 1, its value is 1 by 3. So if I can write it as x plus 2, 1 by x plus 2, then you can see that okay, it satisfies these points. So at x equals to 3, it is 1 by 5, fx is 1 by 5. At x equals to 5, fx is 1 by 7, and so on. Okay, and at x equals to 0, its value is 0.5. Though visually it doesn't seem like it's a 0.5, but for the time being, let's assume it's 0.5. Okay, it is not, y-axis is not scaled properly. Now what we will do is we will find out this area under fx, area under the curve. Okay, so we will find out area under the curve, green shaded region. Okay, so the area under the curve divided by I, which is integration 0 to infinity fx dx, right? And okay, let's see what's the area under this curve. So I can write it as limit k tends to infinity 0 to k fx, and fx is nothing but 1 by x plus 2 dx, right? So if I do the integration, it is limit k tends to infinity ln mod of x plus 2 0 to k, which is basically limit k tends to infinity ln mod of k plus 2 minus ln 2, right? And you know how the log function looks like. So ln x of x, if this is x equals to 1, then it looks like this. So as x tends to infinity, ln x will also tends to infinity, right? So if k tends to infinity, then this term it will tend to infinity, right? So that means this I tends to infinity. That means this area under the curve fx, that means the green region, this green region is tending to infinity, and this blue region, which is basically this a, it covers more area than this green region, right? So you can see this blue region, so it covers some extra area also. So it covers the whole region, the green area covers, and as well as it covers some extra region also. So that means this a is always greater than I, and I diverges, I goes to infinity. That means a should also diverges. A should also diverge. A should also go towards infinity, right? So that means, and as a goes to infinity, that means this y odd L equals to 0 at x equals to 1 should also goes to infinity. This is called the integral test. Okay, so that means it basically proves that y L equals to 0, the odd series for L equals to 0 at x equals to 1 tends to infinity, right? Diverges. And similarly for x equals to minus 1 also you can show, for x equals to minus 1 it will be just a minus 1 multiplication with that, and if these series without a minus sign diverges, that means with a minus sign also it will diverge, right? So for both x equals to plus minus 1, the series will diverge. Okay, so let me then formalize things. So let me write what happens at x equals to plus minus 1. Okay, for L equals to 0, what we got is basically y even at 1, L equals to 0 equals to 1, and y odd at x equals to 1, or rather plus minus 1, L equals to 0, it diverges. Okay, similarly for L equals to 1, y even L equals to 0, sorry, L equals to 1, L equals to 1. Let's see what happens. Okay, so L equals to 1 now. So this is the series. So now if you look at this odd series, okay, here you can see there is a L minus 1 term here, and here also there is L minus 1 term, and if you follow the pattern, so for all the higher order terms for this odd series, there will be L minus 1 term, right? And now if I put L equals to 1, that means those terms will be 0, right? So it is not a power series anymore, it's now a polynomial. We are truncating the series basically. So now we are left with this x only, right? And x at x equals to 1 is 1, right? So this is so basically this odd series for L equals to 1 at x equals to 1 is 1. Okay, so for L equals to 1, the odd series will converge at x equals to plus minus 1, right? But the even series, so you can see there are terms like L plus 1, okay, and if you put L equals to 1, it is still a power series. So we cannot truncate the even series for L equals to 1, and it can be shown that for x equals to plus minus 1, the power series will diverge. Okay, so that means this even series, it diverges at x equals to 1. Okay, it is finite. It is finite. Similarly, L equals to 2, for L equals to 2, y L equals to 2 even, you can see for L equals to 2, so you can see here L minus 2 sitting here, and following the pattern for all the higher order terms for this even series, there will be L minus 2. And now if I put L equals to 2, then the series will get truncated. So it's not a power series anymore, it's a polynomial. So it will have only these two terms, right? And as it's not an infinite series, for x equals to 1, it will obviously converge. It will obviously give me a finite value, right? So basically it is finite. And for odd, L equals to 2, 1. So if you look at this odd series, you can see there is L plus 2 kind of terms. So here are terms like L plus 2, okay. So you cannot truncate the series by putting L equals to 2. You cannot truncate the odd series basically, okay. So it diverges. Similarly, for L equals to 3, the event series will diverge. The event series will diverge at x equals to 1, and the odd series will get truncated and will be a polynomial and will give a finite value at x equals to 1. Okay, because you can see for odd series there is L minus 3, and all the higher order terms in the odd series there will be L minus 3. So only these two terms they will survive. So the series will get truncated and we will be left with a polynomial, and so on and so on. Okay, and as I told earlier that we are interested in only those solutions for which the series at x equals to plus minus 1 will give us finite value. Okay, so for that means for L equals to 1 we are interested only this event series. Sorry, for L equals to 0 we are interested only this event series. For L equals to 1 we are interested only this odd series. For L equals to 2 we are interested only this even series. For L equals to 3 we are interested only this odd series. Okay, so we will not consider this odd series for L equals to 0 and for L equals to 2 and so on, and similarly for L equals to 1 and 3 we will not consider this even series. Okay, so basically what we have is for L equals to 0 we have YL even x equals to 1. Okay, for L equals to 1 we will consider only the odd series, right? So for L equals to 1 y odd 1, so let me call it L equals to 1. X equals to x, right? I mean, if I put L equals to 1, only this term will survive in the odd series. Okay, similarly for L equals to 2, okay, y even L equals to 2x is equals to, so for L equals to 2, if I put L equals to 2, so then these terms they will be 0, so only these two terms will survive, and which is 1 minus which is 1 minus so L is 2, that means 2 divided by 2, and 2 plus 1, that is 3, so 3x square is 1 minus 3x square. Okay, for L equals to 3 we will take the odd series, so L equals to 3, it's because for L equals to 3 and L equals to 1 the even series it will diverge at x equals to plus minus 1, and the same reason for this L equals to 0 and 2 also, like the odd series will diverge for x equals to plus minus 1. Okay. So for L equals to 3 you can see these two terms will survive, and these will be, because L minus 3 present here, so all the higher order terms in this odd series will be 0, right? So basically we are left with these two terms, that is x minus L equals to 3 if I put, then it is 3 minus 2, that is 3 minus 1, that is 2. So 2 cancels because there is 3 factorial in the denominator, and there is a 5. So 3 plus 2 is 5. So 5 by 3 times x cube. So it is 5 by 3 times x cube, and so on. Okay. Similarly, for L equals to 5, the odd series will survive. The odd series will survive. You can find. And for L equals to 4, the even series will survive. Or even series we will consider basically. Okay. So L equals to 4. Okay. So these will be polynomials. It's not an infinite series anymore. Okay. So you can just calculate these values, these functions. Okay. So now these polynomials are basically called the Legendre polynomials. Okay, this PLX subjected to a normalization factor. Okay, so PLX is not exactly this y even or odd, whatever, even or odd, is LX, not exactly same. It is subjected to a factor, normally constant factor. Let me call it alpha. Let me call it alpha L. Okay, and this normalization factor is present because of some special kind of normalization in this Legendre polynomials PL. Okay, this PLX, they required a special kind of normalization, and for that we need to multiply with some scalar factor with these derived polynomials to get the Legendre polynomial. Okay, so what do we mean by normalization? So that I will discuss in some later classes. I mean, in case of vector, what do we mean by normalization is, in case of vector, by vector I mean Cartesian vectors, vectors with direction and magnitude. In that case, normalizing a vector, it means finding a unit vector along that direction. So what do we mean by finding a unit vector in these functions, for in case of these functions? So those things I will discuss in some later class. So for simplification, let me tell you that our requirement here is PL at x equals to 1 is 1. That's our requirement. In order to fulfill this requirement, we need to multiply with some constant factor with these polynomials. After that, we can only tell them Legendre polynomials. Okay. For example, for L equals to 1, for L equals to 0, that P0 x is 1. Okay, which already satisfies this requirement, so we don't need to multiply with any normalization factor. Okay, similarly for L equals to 1, this P1x equals to x, it is basically this is basically y even L equals to 0x, and this is basically y odd L equals to 1x. Okay, and you can see that at x equals to 1, this P1x is already 1, so it satisfies the requirement, so we don't need to multiply it with some normalization factor. Okay, let me tell you again why this requirement, that I will explain later, not in this class. For L equals to 2, this P2x, which is basically this even series, that is 1 minus 3x square, 1 minus 3 x square. Now if you put x equals to 1, you can see this value is minus 2. So it is not satisfying this requirement, and in order to satisfy this requirement, we need to multiply it with some normalization factor. Let me call it alpha 2. Okay, and let me fulfill the requirement and find out the value of alpha 2. So the requirement is p1 is 1. Okay, now if I put x equals to 1 in this expression, it is alpha 2 times 1 minus 3, that is minus 2, which implies alpha 2 equals to this 1 by 2 with a minus sign. Alpha 2 is minus of. So that means our p2 x is half 3x square minus 1. Okay. Similarly, for L equals to 3, our p3x equals to, so for L equals to 3, we should look for the odd series, that is this one. There is x minus 5 by 3 x cube, x minus 5 by 3 x cube. But now if you put x equals to 1, then it is 1 minus 5 by 3, that is minus 2 by 3. It is not 1, right? So it is not satisfying this requirement. It is not satisfying this requirement, and as a result, I need to multiply it with some normalization factor. And to find out this normalization factor, what I will do is, we know that p31 is 1, and now I will put x equals to 1 in this expression, that is alpha 3 times minus 2 by 3, which implies alpha 3 is nothing but 3 minus 3 divided by 2. So then p3 x equals to minus 3 divided by 2 times x minus 5 by 3 x cube, which equals to which equals to 1 by 2 times 5x cube minus 3x. So this is the p3x, and so on. Okay, so these are called the Legendre polynomials, or the Legendre solutions of first kind. Okay, what about the Legendre solutions of second kind? So those are the diverging series for x equals to plus minus 1. That means here I took the even series, right, for L equals to 0. Okay, so there is a odd series present also, L equals to 0. So this is the Legendre function of second kind. Okay, here also there will be an odd series, there will be also a diverging series, which is basically the even series. This is the diverging series. This is the diverging series at x equals to plus minus 1. So this is basically the q1x, this is the q2x, where this q, it represents the Legendre functions of second kind. Okay, but those are not so important, so I'm just mentioning them. I will not be discussing anything more about these second kind of Legendre solutions, Legendre functions. Okay, so now let's talk about this first kind of Legendre functions, or Legendre polynomials. Okay, these are polynomials, these are not the infinite series or power series anymore. So let me plot them. This is the x-axis, this is the y-axis. This is our x equals to 1, x equals to minus 1. This is, let's say, y equals to minus 1, and this is, let's say, y equals to 1. Okay, so then this is, so it is also well defined at plus minus 1. So this is our p0x. Okay, p1x is x, so that means it will be a straight line passing through the origin. and at x equals to 1 all are 1. Okay, this is our p1x. p2x is basically, if you look at the p2x at x equals to 0, it is p2x is 0.5 minus 0.5, okay, minus half, and it is a hyperbolic function, right? X square. That means it starts from here, it goes like this, goes like this. Goes like this. This is our p2x. So you can see there are two zeros of this p2x. Okay? There are 2 points when it cuts the x-axis. It is because p2x is a polynomial of degree 2. So in p2x, in this polynomial, x has a the maximum power of x present here is 2. Similarly for p3x, this is the p3x. This is the p3x. So at x equals to 0, it's 0. Okay. So in the neighborhood of x equals to 0, x cube will be very small. So this minus 3x will dominate. So that means this minus 3x, it looks like this. Okay. And near about plus minus 1, this x cube will dominate. So that means it will look like this. Okay, now if I connect them, it basically looks like this. So this is our p3x, and you can see x has a highest power of 3. That means it's a polynomial of degree 3, and it has 3 zeros. This one, 3 zeros. It is passing through the x-axis 3 times, crossing the x-axis 3 times. Okay, so these are the Legendre polynomials. Now the homework is find out p4x and p5x and plot them. Okay, so in order to do that, so you need to calculate these terms. Okay, and then you need to satisfy with this requirement to get p4x and p5x, and you can now then plot. So that's all for today. So what we discussed is how to derive Legendre polynomials which are finite at x equals to plus minus 1. Okay, and in the next class I will talk about some other methods from which you can also derive this Legendre polynomials. So those will be Rodriguez formula and geometric functions. And after that I will talk about orthogonality, orthonormality, and all other kind of properties of this Legendre polynomials. So that's all for today. Bye.